Yes, we can.
Okay, thank you for the confirmation. Okay, so let's start the next lecture. So last week we stopped at the description of the Einstein's theory of radiation. So we, as far as I remember, we introduced the effect of spontaneous emission. Am I right, or just correct me if I'm wrong?
Yes, we did.
Yeah. So just as a short reminder, so spontaneous emission, we have a two-level system, and the atom can be spontaneously emitted with a random phase direction polarization. Absorption, so the atom absorbs the energy and from the incoming field and moves to the upper energy level, and stimulated emission when the photon is in the state 2, and due to the external radiation from an external field, the photon stimulates emission of a second coherent photon, which has the same polarizations in direction, phase, and frequency as the incoming photon. So we have two copies of the same photon that was incoming from this side. Okay, and we can also now assume, when we know the three main elementary transitions that can occur in atomic systems, we can now assume, we can now maybe think if we can build a medium that could amplify light waves, incoming photons. So for that, we can just assume kind of a, let's say, container with the medium, so with the length L, shown here, right? And we have the incoming plane wave from the left side with the intensity I and the area of the cross section S at a frequency, let's say, E0, right? And the medium consists of atoms with two energy levels, and we have some of the atoms are on the upper level, so we have some density, some distributions of atoms in the upper level, and we have some density on the lower level, so some of the atoms are on the ground level. So now we can now analyze what will be the increase of the optical power of this intensity here, I, after passing through this medium. So for simplifying that, we can just slice this medium into smaller parts with elementary length dz, shown here. So we will think what conditions have to be fulfilled to have amplification of this wave. So it can be shown that the increase of the power, so let's say di, can be expressed with this formula, where I is the incoming field and 2 is the density of the atoms on the second energy level, and n1 on the first level. B is the Einstein's coefficient, and we can we generally assume here that these two coefficients that were previously for emission and absorption, they are equal, and this is actually true for lasers in real life. So we can make this assumption just for simplicity. And this is, of course, the Planck constant, the frequency, and the length of this elementary length dz of this medium. So this formula allows us to say if our medium will amplify the wave. And I think you can already see what will be the condition to have amplification, so that to have a positive part here in the brackets. Just for making it even simpler, we can just say that this is a constant. I mean that this is a parameter that is specific for a specific gain medium. So just a gain parameter G, right? So the G parameter would be the difference between the densities of the atoms on certain energy levels, and this B parameter and the Planck constant at frequency. So now it's simpler, right? So we have only the dI, so the increase of power equals to I, so the incoming wave times the gain coefficients times the propagation length. So we are now, let's say we can rewrite it, and we are looking for the gain function. So this, as you can see, this is a differential equation, and the solution is a function that describes the intensity of the wave that is passing through the gain medium, and this is this function here. So we have the I0, which is some incoming intensity at the beginning, at the entrance of the gain medium, and we have an exponential function, and this is proportional to the gain and to the propagation length. So we can see already that when the gain G is positive, then the wave will be amplified, and if G is negative, then the wave will be attenuated, right? So let's firstly consider that the wave is attenuated, so G is equal to 0. So we start from, we start here from the value I0 at the input, right? And during propagation, the beam is exponentially attenuated, right? Proportional to the propagation length. Because the gain function is negative, so the gain function will be negative if we have more atoms on the level N1. So if N1 is bigger than N2, right, then the result here from this difference in this bracket will be negative, right? So the gain function will be negative. So the N2 is the population, the density of atoms on the upper energy level. So the problem is that in thermal equilibrium, and this is something that we know from the Boltzmann distribution, N2 is always smaller than N1, which means that in thermal equilibrium, we always have more atoms in the ground state, in the lower energy level, right? So the lower levels are always populated more densely than the upper levels if no other process takes place. So the conclusion is that if the medium is in thermal equilibrium, there is always only attenuation. There's no way to have a positive gain because N1 is bigger than N2. But if we manage somehow to increase the density of atoms on the second energy level, so N2 would be bigger than N1, then we will get amplification. So again, we start from the initial value I0 at the input, and then we have amplification. Of course, at some point we will reach some kind of saturation, but this is something that we will maybe discuss later. But generally, this is, let's say, exponential, right? Given by this equation. Yeah, but the main problem now is how to make the situation where N2 is bigger than N1. And this state is kind of let's say, unusual state for typical real life systems, because it requires that more than 50 atoms totally in the gain medium is in the upper state. And this quantum state is called population inversion. So you can already see from the name that this is inversion. So this is something that is unusual, because this is just something which is inverted with respect to the natural state of matter. So population inversion is the condition in which we have more atoms in the upper energy state, so more than 50%. So if we have a container where we have 5 atoms, so we need to have 3 on the upper state and 2 in the lower state, and this means that we have population inversion. And in this kind of medium, the gain function will be positive, and we will have amplification in this kind of medium. Yeah, so this is exactly that what I said. But the main question is how to achieve population inversion in atomic systems. And in laser technology, we call it pumping. So this is basically delivering energy to the system, and this can be done in several ways, depending on the type of laser that we are considering. So in for example, solid state lasers or fiber lasers, we use so-called optical pumping. So we deliver the energy just by using another laser, right? So we can have a solid state laser, like, let's say, a crystal doped with neodymium, for example, neodymium YAG. So this is a yttrium aluminium garnet crystal, which is doped with neodymium atoms. So we just illuminate this crystal with another laser beam at the wavelength of 808 nanometers in this particular case. And by that, the neodymium ions will absorb 808 nanometers because this matches the this delta E, right? So the this energy gap corresponds to this wavelength. So the neodymium atoms will be excited to the upper state, and we will achieve population inversion. So this is an example of a solid state laser. We will, of course, discuss this in more detail in maybe 1 or 2 weeks. In case of gas lasers, we use electric discharge in gases. So we connect a high voltage power supply to the gas, and we obtain the discharge. And by that, we just generate a lot of energy that is absorbed by the atoms, for example, by the atoms of neon, for example, that can generate then light at 632.8 nanometers, which is the wavelength, main wavelength of neodymium lasers. In semiconductor lasers, we also can excite them either by optical pumping. This is also possible, or the most common approach, just pumping electrically. So we just apply the voltage to the electric field, the voltage to the semiconductor, and we induce the flow of electrons through the p-n junction. So a more philosophic question: is heating a good idea to deliver energy to the atoms? Yeah, I think you already should know that this is not a good idea, and this was explained in the previous lecture, that delivering energy to these kind of atomic systems with heat, when we consider these energy gaps corresponding to visible or infrared transitions, like in typical lasers, this makes no sense, because the probability of exciting the atom from the lower to upper energy state when we just heat the medium by 300 degrees is at the level of 10 to minus 5, maybe 10 to minus 8. So this is a very low probability, and there is no chance that we will achieve population inversion by just thermal That's just by heating. So the delivering of energy is called pumping in lasers, and each type of laser requires different types of pumping. So we will also go through the pumping mechanism when we will describe the specific types of lasers. So very often gain is expressed in logarithmic scale. So this is also something that you should be aware of, that as electronic engineers, you're familiar with decibels. And we also in optics express the gain in the logarithmic scale. So yeah, it's obvious that when we have the input intensity, the output intensity, then the gain is just the relation of the output to the input in the linear scale, right? But if we want to convert it to the decibel scale, this is the right formula to do that. And if you want to convert it back to the linear scale, you can also do it with this formula. So the dB scale is very convenient to express gain, because we just replace multiplication just by simple adding and making very simple calculations. So it's good to be familiar with these units. So you should know that, yes, you should know the elementary gains, like 3 dB corresponds to 2 times of amplification or attenuation, right? 10 dB it means 10 times, 20 dB 100 times, 30 dB 1000, and so on. So when we speak about high gain values, so in lasers we often have gains at the level of 30 dB. So these are large numbers. So it's just, for convenience, it's just easier to express them in the dB scale. So I just encourage you to make some basic calculations at home, and just to be familiar with this scale, and also with the unit of dBm, which is just the which expresses the power, not the relation between the input and the output, but just the power. So 1 dBm corresponds to 1 milliwatt of power, right? Oh no, not one, yeah, and 3 dBm 2 milliwatts, and so on. So this is basically, yeah, this is what is also often used in optics, and you will see it on the laboratory, for example, when measuring the parameters of fiber laser. Okay, so we considered an amplifier. So we have the input, we have the output, and when we have positive gain, we have amplification. So this is an amplifier, but as I said, a laser is a generator, right? So we don't need to have an input. So a laser has just an output. So I think for you, like electronics designers, you should already know how to make a generator out of an amplifier. Can someone tell me how to do that?
We just reverse the flow.
No, if we reverse it, it's bidirectional. So you can either, yeah, if it's symmetrical, you can put the input here and have the output here.
So add positive feedback?
Yes, exactly. So we need to add the positive feedback. So we just take a portion of the output and feed it back to the input, right? And by doing that, yeah, I think I have even, yeah, I have the slide. So if we do that, we just seed the input with the output signal. So we will cause just oscillation, right, of our signal in the system. And then we basically don't need, after some time, you could even turn off this input and this system will generate anyway, right? So this often happens in like acoustics when you have some positive feedback between the microphone and the loudspeaker, and you see this very inconvenient noise from the loudspeakers, right? So when we feed the output signal, provide the positive feedback, we can make this oscillation possible. So we make just basically an oscillator, right? So this often happens in electronics if you want to make an amplifier and it starts to be unstable, and it sometimes becomes a generator. So the same applies to optics and let's say quantum amplifications, quantum amplifiers, so quantum optical amplifiers, right? When we have this amplifier with our input beam and output beam, and we can put just a mirror at the output that partially reflects the beam and partially transmits. So this might be even, let's say 50%, that doesn't matter so much. So this is just a beam splitter, right? So we have 50% of the power here, and we reflect it with another mirror, another one, and another beam splitter, so that the portion of the output signal is again directed to the input of the system. This will start to oscillate, right? This will be a generator, and then again we can even remove the input beam, and if we still have the positive gain, so we need to remember that this is positive. So we still need to deliver energy to the system to have this positive gain, right? We need to provide pumping. We will have emission from this system. Of course, we can have, since this is symmetrical and works in both directions, the emission can occur in both directions. So we will have two outputs in this system, like clockwise and counterclockwise. So just as a digression, we can put a isolator into this kind of system and provide unidirectional operation. And this kind of system is called a ring resonator, because this is called a resonator in optics, right? And this is one of the most typical arrangements of an optical resonator, which is the ring configuration. However, the most common configuration is a linear resonator. So if we now imagine that we have this ring and we have these two mirrors, and we just move them both closer to the gain medium, right? So we just move them here, right, and here and here, and finally we can move them so close that both beams traveling in both directions pass through the gain medium, right? But we can go even one step further and put just flat mirrors placed parallel to each other. So the beams traveling in both directions, they travel the same path. And this is the most common and most popular, widely used resonator in laser optics and laser technology, called the Fabry-Perot resonator. And we will describe this in more details today. So to build a laser, we need three basic ingredients. So we need to have the gain medium. So a gain medium with where we have atoms and we can have the positive gain. We need the optical resonator, so a Fabry-Perot or a ring resonator, so something that provides us the positive feedback, right? Because this is just a positive feedback here, and the same applies here. So a portion of the light will be extracted from this resonator, but generally most of the light will be bouncing between these two mirrors. So these mirrors provide the positive feedback. So this is the feedback. And the pumping source, of course, right? So this is the energy that is delivered, like just a power supply, right? So this ensures us that we have this positive gain because we deliver the energy to the pumping source. So each laser has to have these three features, and you cannot build a laser without one of them. Someone might say that I can build a laser without a resonator. Yeah, this is true. But anyway, you will need to have some kind of feedback, which will be just even some parasitic reflections can act as a resonator. So this slide here will just summarize the in very simple words, just to make sure that you have the intuition and just know in very basics how this process looks like. So we start with our gain medium. So this is either a gas medium or a solid state or whatever, just a medium that contains atoms of some element that is optically active. So it has the proper structure, energy band structure, and it has the property of emitting photons and absorbing photons, right? So you can assume that it might be a crystal with neodymium ions, for example, neodymium atoms. So we put this resonator around our gain medium. So just two mirrors. One mirror has a reflectivity of 100%, so it will reflect everything. And the other mirror has a lower reflectivity of less than 100%, so it will transmit a portion of radiation, right? So it will not reflect everything. So now if you have a system like that, we now introduce the pumping, right? So we turn on the source of energy, the pump. So we deliver the energy to the atoms that are here in our gain medium. So what happens now? We will see that our medium will absorb, right? So we have the first elementary transition, which is absorption. Our atoms will absorb the energy from the pumping ions. So we will move them into the second energy level, right? So they will jump to the second level because they absorb the energy. So since they are already on the second level, after some time we will have the second elementary transition, which is spontaneous emission, right? So the atom will just decay to the ground state and it will emit spontaneously a photon. As you know, spontaneously emitted photons are random, so they have a equally there is an equal probability of emitting photon in each direction. So the direction is completely random, so they can be directed in any direction. They can have random phase polarization. However, if we have enough atoms in our medium, they will emit a lot of photons, and it might happen that some of the photons will be emitted in the good way, right, in the good direction, so that they will just be directed to the mirror. So the rest of the photons will just be emitted in any direction, so they will just exit the resonator, just escape it. But let's assume that some photons, like 3 photons in this case, they will just go to the right direction, and they will hit the mirror. And the mirror will, of course, reflect all the 3 photons. And now these 3 photons again meet with the atoms that are here in our gain medium. So we will have the situation where we have atoms at the upper state, because we still pump it, right? We still deliver energy. So these atoms are still excited. And then we have the photon incoming from this side, right? So we will have stimulated emission. So the atom will decay to the ground state and emit 2 photons. So from 3 photons, we will have 6 photons because of spontaneous emission. And now these 6 photons travel again the same direction, and they hit the second mirror, and the second mirror has less than 100% reflectivity. So we will have emission. Yeah, these red arrows shouldn't be that far. They should be here. So this is just a mistake in this animation, but doesn't matter. So the laser beam is the green one that will escape from this resonator, and then these 6 photons will be reflected again, and then they will produce 11 photons, right? Because each of the atom will produce a coherent copy. So I think this is just a very simple way of understanding how the laser works. Usually this requires, so maybe the main message here is that laser emission starts from spontaneous emission. So when we turn on the power supply, turn on the pumping source, our atoms start to emit spontaneous photons. And then some of these spontaneous photons will be lucky enough to hit the mirror and to just be reflected and again hitting the atoms in the medium, and they will just stimulate the coherence stimulated emission. So to obtain a stable steady state in the laser, this requires usually a few hundreds of these kind of round trips. So we call it round trip, right? So the way that these photons pass from one side to another and going back again to the first mirror. So after a few hundreds of round trips, the laser will emit a stable output beam at this constant power with stable parameters, and we will obtain this kind of steady state inside this resonator. And this of course depends on the design of the lasers, because sometimes this will be faster and sometimes it will take a longer time, but you can already guess that since this travels at the speed of light, so a few hundred bounces, it takes like, I don't know, maybe microseconds to have the laser running. So since you already know that laser is a generator, so we have this oscillation of light inside the resonator between these 2 mirrors, then you already should see that this acronym is basically wrong, because the laser is not an amplifier, because we don't need any input signal, right? Because an amplifier amplifies some input. In the case of the laser, we don't have any input. We just generate, and the beam is oscillating inside in the resonator. So we should replace the word amplification by oscillation. But then we would have a problem, because the acronym would be loser. So this would be really bad for science, because no one wants to work with losers. But a lot of people want to work with lasers. That's why probably people who invented this acronym decided to use the word amplification. But this is a little bit misleading, because this is not an amplifier. However, of course, there is amplification of the photons in the gain medium, but just please remember that the laser is not an amplifier, but an oscillator, a generator. Do you have any questions regarding this part? Maybe something was unclear.
Yes, I have one question. So can you come back one slide before? So my question is, this source of pumping, is it constantly on, or?
Yes. Basically, in most of the cases, you can assume that this is constantly on. There are some cases of specific types of lasers where this is modulated, in amplitude modulated, but generally this is constant.
And for example, if we will provide some energy to the laser and then turn off the pumping source, how long it will still work with the amount of energy we provided?
Yes, that's also a good question. So this will work that depends on the design, but usually this is a time scale of up to maybe microseconds, maybe milliseconds in the best case, but usually microseconds. In some cases, even nanoseconds. but this is the time scale, just more or less, because this is also what you're saying about. This is one of the methods of making pulsed lasers. I will of course talk about that later. But when we have our laser and we have our pumping source, it might not be a continuously driven constant power source, but something which is pulsed. So then the laser medium is pumped, and at some point the pumping just turns off, and then the energy is just released by the gain medium in the form of the pulse, which has a different shape than the pump because of the dynamics of the gain medium, but the duration of the pump will be at the level of nanoseconds to microseconds. So this is related to the design of the resonator and the lifetime of the energy levels inside the laser. But yeah, you will just almost instantaneously see that the power will just shut down at the output. Okay, so I will go move on. So now we will switch to a little bit about these resonators. So I mentioned about the Fabry-Perot resonator. So the name comes from the names of the two inventors, so Charles Fabry and Alfred Perot. As you can guess, French scientists. So the arrangement is really simple. So these are just two parallel mirrors separated by a distance of L, right? So we have two mirrors. So let's say this is the first mirror here, right? And this is the second mirror here, M2. So when we analyze this kind of mirrors, we need to take into account that we have some incoming field, incoming electric field, right? So incoming light, let's say, right, from that side. And we need to remember that some of the light will be reflected from this mirror, from this side, and will not enter the resonator. So this will be written as ER, reflected, but some of the light will enter inside this resonator. So this will be the EW plus because this will propagate in the right direction here along the optical axis. And again, if this beam reaches the second mirror, then it will be reflected from this mirror, right? So we will have the field EW minus, which is propagating in the back direction. and some portion of this field will be transmitted through this mirror, and this will be our output. So this is the ET, so E transmitted. And we define the reflectivities and transmission of these mirrors. So R and T. This depends on the technology of fabricating of the mirrors. There exist mirrors that have 100% reflectivity, like metallic mirrors, let's say close to 100%, but I mean they have 0% transmission, and they have, let's say, some losses, but close to 100% of reflectivity. There exist mirrors that have less than 100% reflectivity, so this depends on the design. But the more precisely given reflectivity, the more expensive the mirror is. So for example, if we want to buy a mirror that will have 99.9% reflectivity, or you want to have 99.8%, this makes you a difference of let's say €1,000 on the price of the mirror. So this is a huge difference. And in the Fabry-Perot resonator, we of course assume that in our further analysis, we will assume that the reflectivity and transmission is equal to 1. So we have no losses in the mirrors. So now we can write a function that describes the transmission and the reflection from this kind of resonator. So I am just giving you the solution. We will not go through the to the way how it was derived, but there is a function that describes how the light will be transmitted and how the light will be reflected from the cavity, because we need to remember that when we have this resonator with these two mirrors and we just illuminate it with light, then we consider this as a, let's say, black box, and we have some transmission, but we will have some reflection. So this is the reflection and this is the transmission of this system, right? And what you can see here is that we have the reflectivity coefficients of both mirrors, and we have also this this kind of a phase term here. So this is dependent on the frequency. And if we plot the transmission function as the transmission as a function of frequency of a Fabry-Perot resonator, right? So this is the Fabry-Perot, and we have our input, and we have our output. So this is our T versus the frequency. You will see that this function has some peaks, has some periodically repeating maxima with a period of C over 2L. So here you have written the frequency of consecutive maxima, Q minus 1, Q, and Q plus 1. And you can see that they have all this C over 2L term, where C is the velocity of light and L is the length of the resonator. So the transmittance function of the Fabry-Perot resonator in the frequency domain looks like a comb function. So this is just periodic maxima equidistant. So the distance between them is constant, and it only depends on the length of the resonator. And if we look at the reflection, then the reflection is exactly the opposite, because transmission plus reflectance needs to be 1. So the reflected beam will be exactly the opposite. So what does it mean? It means that if we want to transmit some optical frequency, some optical beam at a given frequency through this kind of resonator, we need to match these resonances, right? So our laser beam that wants to be transmitted through the resonator needs to fit into one of these maxima. And you can guess that they start at 0 and they end at in infinity, right? Because this is just infinitely broad. And these maxima are spaced by C/2L. So the frequency of the maximum number n is just given by the n times C/2L. So this is, of course, an empty cavity. So this is a resonator that is empty, right? Without, just filled with air or vacuum. And what is important here is that the width of these peaks depends on the reflectivity of the mirrors. So depending on the reflectivity of the mirrors, these peaks can get more narrow. So on this slide, you see the calculated transmittance of a Fabry-Perot resonator for different reflectivities of the mirror. So you can see in the case when the reflectivity is very low, like 4%. So this is a blue one. So you see that the modulation is not too high. This is just kind of a sine wave. So these resonances are quite broad. And basically this resonator will transmit everything because this this sine function is, it has an offset from the 0 frequency, right? But if the mirrors are better, like 99%, then we have the blue one, the blue situation. Then our resonator will not transmit anything, which will not fit into these resonances. Okay, so only optical frequencies that fit these resonances can exist in the resonator. And the better the mirrors are, the narrower these resonances. And the spacing between the consecutive resonances equals C/2L. And L is the length of the resonator and C is the speed of light. I hope this is I hope this is easy for you to understand. I hope if something is unclear, just interrupt me. Now maybe I will explain where is it coming from. So the origin of these resonances is coming from the fact that in this kind of resonator, the only beam, the only configurations of the electric field of the optical wave that can exist needs to be, they need to fit into the length of the resonator. So this needs to be a integer multiplier of lambda half. Okay, so let's assume that this is our first order of the wavelet that is fitting this resonator. So this is lambda half, right? So we have only the positive half of the wavelength, the wavelet, and here we have the reflection, and the other one is reflected here. This is 2 times lambda half, so this is the full lambda. So we have the full wavelength fitting into this resonator. We cannot fit into this resonator something that would be like here, because this wouldn't be a, or here, this wouldn't be a full half of the wavelength, right? So from these resonances, we know that this difference between the frequency should be C over 2L, because this can be seen here. The waves need to fit into the length of the resonator. So L is the length of the resonator. So the length must be just a multiplication of lambda over 2. So if lambda is C over the frequency, then if we put this here, we will end up with a solution for the frequency of the mode number of the resonance number Q. So this will be Q times C over 2L. And if we want to write the Q plus 1 frequency resonance, this will be Q plus 1 times C over 2L. Yeah, so this is the there was a question in the chat. I see it now. Do reflectivity also changes with big changes in frequency? Some materials are opaque and visible. Yeah, that's a good point, and it's of course true. Maybe this is something not strictly related to what I'm now talking about, but I can answer the question. So if we look at the reflectivity of typical mirror as a function of the frequency, or maybe we should say wavelength, because this maybe will be easier now to understand it in wavelengths. So typical dielectric mirrors have the reflectivity like that, for example, right? So they have some peak reflectivity and some bandwidth and some kind of suppression ratio of the rest. So this acts like just a filter, right? But some of the broadband mirrors, like metallic mirrors, so let's say metallic, like silver, gold. So gold is wasted on jewelry, but gold mirrors are really beautiful because they are pretty cool. Maybe you know that the James Webb telescope, the famous one, it has golden mirrors in its design, because gold has a very high reflectivity in the middle infrared range. Since James Webb telescope is working in the infrared range, they needed to have a very high reflectivity in the infrared region. But with gold, there's also some problem that gold will have some lower reflectivity in the visible. So it very often happens that these materials also have some resonances at some wavelengths or some local peaks. But generally, we divide mirrors into broadband mirrors, usually metallic, or dielectric mirrors that have narrower bandwidths, like this one, but very high reflectivities, but only in the peak, right? So yeah, I hope that this answers your question about the about the reflectivity. I don't know. Do you see the slide now? I just want to make sure.
Yes.
Yeah. Okay. Because when I am switching between the slide and the board, then sometimes I have trouble with going back to the slide. Okay. So now we can define the main parameters of the Fabry-Perot resonator. And the first one is already was already explained. So this is this frequency difference between two consecutive resonances. So we already know that the difference between the frequency Q and Q plus 1 equals to C over 2L. C, speed of light, and L is the length of the resonator, right? So this is called free spectral range, FSR. So you need to remember that. And then here you have some examples of the values of FSR for different resonators. So in case of very small lasers like semiconductor lasers, the length of the resonators are really small, like millimeter scale. So then we have very large FSR in the range of gigahertz. But in typical lasers like gas lasers, fiber lasers, sometimes solid state lasers, the resonator has the length of meters. So then the frequency is in the range of some megahertz. So let's say 100, 150 megahertz. So the length of 1 meter corresponds to 150 megahertz. So when we look at the transmittance of the resonator as a function of the frequency, it will have these consecutive resonances separated by 150 megahertz. And this is why it is important to also be able to understand the switch between the light in the wavelength domain and in the frequency domain, okay? Because we, in the case of resonators, we always use the frequency domain. So the conclusion from that is that if you want to transmit light at the frequency that would be, let's say, here, this is not possible, right? So these waves could not, the wave laser beam at this frequency here could not exist in this kind of resonator because it doesn't fit the resonance. So this would be reflected by the resonator, okay? Okay, the second parameter is the line width of this resonance, right? So there is an equation here, number 2, that defines the so-called empty cavity line width. So this is the line width of the resonance, the width of the resonance, measured at the full width at half maximum, right? So this is the half of the intensity. So we define the maximum and we measure the width of the resonance in its half. So this is the so-called FWHM, full width at half maximum. We will use this term very often. And you can see what factors contribute to the line width of the resonance. So we have C over 2L. So the length also is contributing to that, but mostly the reflectivities. So the bigger the reflectivity of the mirrors, the narrower the resonance. Okay. The third parameter is the Q factor. And the Q factor is, from the definition, this is the frequency of the resonance of the selected resonance, let's say μ0 here, divided by its width. So you have an example. For example, if we have a resonator that has the reflectivity of 100% in one mirror and the other 99%, length of 1 meter. So at the wavelength of 632.8 nanometers, which corresponds to the frequency of 474 terahertz. So this, if we recalculate that, then this is equal. We have the Q factor of 10 to the 9th. So this is a very large Q factor, typical for gas lasers. And the line width of the resonance, so this is what we had here on the previous slide, will be around 0.5 megahertz, 480 kilohertz. So you now see the relation between the width of the resonance and the spacing between the resonance, because the spacing would be 150 megahertz in this case, if this is a 1 meter long laser. But the width of the resonance will be 480 kilohertz. So you see that there's a lot of empty space between these modes, between these resonances. Okay, and the last parameter defined for Fabry-Perot cavities is the finesse. So the definition of the finesse is the free spectral range divided by the line width. So this can be also expressed using this equation. However, yeah, this is more convenient, and it's enough to know this. So the typical value, for example, for the previous case, when we have this 1 meter long laser with 150 megahertz of FSR and 0.5 megahertz of the line width, the finesse equals 300. So 300 it's not a huge finesse, just if we compare it to other types of lasers. So just to give you an impression, yeah, 300 is completely typical for gas lasers. But if we want to have a cavity that is used as a very stable frequency reference, because if the line width of the cavity is narrow, then we can more precisely define the center frequency, right? The center frequency of the cavity. So we are looking for very narrow resonances. So for that we need high reflectivity mirrors and high finesse. So sometimes there exist cavities that have finesse at the level of even 300,000, for example. But the value of 300 is just very typical. And I have also just a digression how to actually measure the cavity finesse. Maybe this will be interesting for some of you. So from the definition, this is the FSR divided by the line width. So measuring of the FSR is very easy because we just need to measure the length of the laser. But the measurement of the width of the resonance is quite complicated, and it's not so easy. So that's why we have some kind of non-direct method of measuring the finesse, just by a so-called cavity ring down measurement. So this is the cavity ring down. We modulate the laser that we are using for the measurement, or we just we can generate just square pulses or just shut down the laser at some point. And then we measure the decay time of the cavity using a photodiode and an oscilloscope. Because if we couple light into this resonator and then we turn it off here, right, on the input, then we will still have some light existing in the cavity. So this was also one of the questions before, right? We will still have some light traveling here, and it will take some time, some round trips, before all the photons will exit this resonator, and the resonator will be fully empty of light. And this happens at a kind of a decay time that is given by a exponential function. So this is how it looks like at the output. This is a real oscilloscope signal. So here the laser source was turned off, right? So this was, we had still some power at the output of the resonator, and here we stop the laser, and we observe that the power at the output is dropping and reaches 0 after some time. So we can just make a fit of this slope. So this is just an exponential fit, and from that we can calculate the finesse, because the finesse is proportional to this time constant of this decay time, and it is shown here. So this is C over 2L times 2 pi times tau, and tau is this decay time. So in this case of this measurement, you see that there was a cavity of finesse equal to 300,000 something, and the decay time was 40 microseconds. And of course, you can guess that the lower the finesse, the shorter this decay time will be. Okay, so but this is just a digression about finesse measurement, and I thought this is worth to mention when we will talk about finesse. So the summary of these parameters, and it is really good to know them and to be able to write these formulas and to understand what is going on here. So the first one, the most important one, free spectral range, C over 2L, the line width of the cavity. So the free spectral range was the difference between two consecutive resonances, the line width of this resonance, the Q factor, and the finesse. Okay, now we will move on to more like geometrical properties of resonators. So now we were speaking about the frequency, about the parameters of the resonator in the frequency domain. And now we will switch a little bit to the geometrical properties and the spatial properties of the resonator. But to do that, I will maybe say a few slides about laser beams, about Gaussian beams. So generally, laser beams and their propagation and their behavior can be described by the Gaussian distribution. And the Gaussian beam is the definition of the Gaussian beam is just the ideal, mathematically ideal, perfect laser beam in general. It means that Gaussian beam, an ideal laser beam, has its intensity profile described by the Gaussian function. So in this case here, labeled as TM00, you see just the fundamental Gaussian beam and its intensity distribution. It's spatial, the intensity distribution. And you see this is just a kind of a Gaussian function, right? So if we look at the cross section of the intensity profile as a cross section, this will be also described as a Gaussian function here. If we look in both axes, we will have this Gaussian distribution. So we have the maximum intensity in the peak in the middle, and then we have less intensity on the rest of the beam. And if now this kind of beam is propagating and we focus it using, for example, a lens. So we put a lens here, just a normal lens. So the beam, this kind of beam will be focused by this lens, and these red lines show the path how the beam will propagate after this focusing. So there are some main parameters of this Gaussian beam. So the main parameter is the waist, W0 here. So the waist is the radius of the beam in its smallest point. So this is something that you would say this is a focal point, right? So the smallest point along the optical axis. And please remember that this is not the diameter, but this is the radius. So to give you an impression how small this can be, the limit is the diffraction limit, so the wavelength is the limit. So it might be micrometers in diameter. So when we know the waist, we can also calculate the radius of the Gaussian beam at any point, at any position z, because since this is a Gaussian distribution, then we can easily predict this propagation because this is known, right? We also defined the so-called Rayleigh range, ZR. So the Rayleigh range is the length where the beam gets bigger by a factor of square root of 2. Okay, so we have this times W0, which is the waist. So usually this corresponds to some micrometers or millimeters of propagation. And we define also the divergence of the beam. So this theta angle. So this defines how the beam is diverging. So how it is getting bigger during propagation after the focusing, after passing the focal point at the waist. And as I said, when we know the waist and we know the Rayleigh range, so we just need to know. Sorry, we just need to know the radius of the beam at two spots. Then we can already fit a Gaussian beam. So by having 2 points, we can already calculate the spot size at any at any point of our optical axis. So this W z function enables us to calculate the radius of the beam at any point where we want. The Rayleigh range is defined as pi times squared waist radius divided by the wavelength. So if we now replace the z with z0, so the Rayleigh range, then you will get this square root of 2. The radius of curvature is also behaving. This is maybe not so relevant, but the radius of curvature of the wavefront is also behaving as a quite unusual function. But what is important here is that we have a minimum at the Rayleigh range, and at 0 distance, so in the waist, the radius of curvature is infinitely big. So this is a plane wave. So when we focus a laser beam into a point, into the focal point, the waist, then the radius of curvature of the wavefront is infinitely big. So this is a plane wave here. Then after passing this point, of course, we will have some radius of curvature of the wavefront. Regarding the divergence, there is a parameter that is called m squared, which defines how far our beam is from an ideal Gaussian beam. So for an ideal Gaussian beam, the m square is equal to 1, right? So we have a situation like here, so that the divergence of the laser beam can be easily calculated when we know the wavelength and the waist. So then we can calculate the divergence, the theoretical divergence. However, this applies only to ideal Gaussian beams. In real life, we often have non-ideal beams. And then we can measure the m square parameter that will show us how far from the ideal Gaussian beam we actually are. And to do that, there is a procedure of measuring the m square parameter. So basically, the measurement setup is quite easy, and I think you might have this exercise on the laboratory, but I'm not sure. So to measure the m square, you just have the laser and you have the lens. So your beam from the laser is focused. So you have this focal point, and you have the waist here. And then the beam diverges, right? And we measure the diameter of the beam at several points here. So for example, here, 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 and around the waist, and then somewhere else. And then we fit a function that is generally it's written in the norm how this function should look like. And from this fit, we can extract the values of the waist, the Rayleigh range, and the m square. Basically, this is kind of a Gaussian function. So we just look at this fit and compare it to a ideal Gaussian distribution at a given wavelength. And by that, we just compare it, and we can extract the value of the m square. So usually these m square values are for just if the laser is good enough, then the m square is usually less than 1.2, so which is really close to a Gaussian beam. But if the m square is let's say larger than 2, then it means that it's not a fundamental Gaussian beam anymore, because it doesn't behave like a Gaussian beam. So I already said about the beam profile, which is which is described by a Gaussian function. So the transverse intensity profile along the radius, this is just a Gaussian function. So we have the maximum intensity, the peak in the middle of the beam. And we can take a look at the cross section in both axes, right? So usually we look at y and x axis. What is important here when we speak about the diameter of the beam, because we either use radius or diameter, that doesn't matter, but it's basically the same despite the factor of 2. When we speak about beam diameter, in case of beam profiles, we don't use the full width at half maximum. Rather, we use a beam diameter that is defined at not 50% of the width, but at 13.5% of the width. So this is basically 1 over e squared times the intensity. So when someone says that my beam has the width of 1 millimeter, he doesn't mean the full width at half maximum, but the 1 over e squared width, which is here at 13% of the intensity. Don't ask me why. It's just so, and we just do it. Probably there are some reasons for that. Okay. Maybe I will skip this because this is not so relevant. So generally, why are we speaking about these Gaussian beams? Because this makes things really easier when we understand how these Gaussian beams propagate, and also in the context of optical resonators. Because in a resonator, we will also have a Gaussian distribution of the intensity profile. So this is an example of a so-called confocal resonator. I will just explain you in a minute what does it mean. So these mirrors have a radius of curvature. So these are not flat mirrors, but they are curved mirrors. So these mirrors focus the beam. So they act as lenses, right? So they have the ability to focus light. So this distribution here of the optical field inside this resonator will be also described by the Gaussian function. So each resonator will have its own solution of this field inside this resonator. So when we want to transmit light through this resonator, if we want to couple the light into this resonator from the outside, we need to match this intensity profile. So we need to calculate the lenses that we will use here in the front of this system, so that our beam will just overlap with this distribution here, right? And then at the output, we will have something like this. Otherwise, if we don't do it, because if we do it in the way like this, then our distributions will not overlap, and this will cause us non-optimum transmission through the resonator. And this distribution inside this resonator, this field, is called mode. So this is the mode, the transverse mode. Transverse mode. So this is basically the geometrical distribution of the field inside the resonator. So let's now assume, let's now analyze this confocal resonator case, and we will go back to these transverse modes. So a confocal resonator is a very simple type of a resonator, but it is good for teaching reasons, and it's also mostly widely used, I think. So confocality means that the radiuses of curvature are equal to L, so to the length of the resonator. So maybe I don't want to confuse you, but these R's here don't correspond to the reflectivities, but the radiuses of curvature. So maybe I should write small letters, maybe. So this is the radius of curvature. So the focal point is ideally in the middle of the resonator, because the radiuses of curvature are equal to L, and both mirrors have the same radius of curvature. So this is the so-called confocal resonator. And in this kind of confocal resonator, there exists the so-called eigenfunctions or eigen values. So these are the solutions of the optical field, the electrical field, basically, that can exist in this resonator. So what I have shown you before on 2 slides back, this distribution of the field inside this confocal cavity, right? This image here, this was the fundamental mode TEM00. So this is the TEM00 mode, the fundamental mode. fundamental transverse mode. So it means that if we look from this direction at the beam that is going out of this resonator, it will look like this. So this will be just a round spot, right? Just a Gaussian beam. So this is the fundamental mode. This is one of the solutions. But there exist more solutions depending on the probably alignment of the resonator. There can exist more solutions like higher order modes that can exist in the system. So the other orders are like TM01, 02, 10, and so on. So these numbers, they indicate how many minima we have in each axis. So here we have one minimum, so 1, 0 crossing, let's say. Here we have 2, so that's why this is TM01 and 02. When we have the 0 crossing in the other axis, then we have TM10, 20, and so on. When we have 0 crossings in both axes, we have TM11 or TM22, like here. So this basically means that what you see here, these are the images of laser beams, just cross sections that you will see at the output of the laser, if the laser inside generates these transverse modes, these higher order modes. So on the next slide, you can see real images of transverse modes that can be generated from a gas laser. So you can see that it can generate like a TM00 mode, but it can generate TM10, 30, even 50, 11, 21, and so on. So these are just the images taken from by a camera of the laser beams at the output of the laser. So it means that this field distribution exists inside the resonator. So it could be understood that we just have 6 independent beams inside the resonator, just in fact. There exists also some kind of superpositions of higher order modes and the fundamental modes, like here. Depending on the construction of the resonator, for example, in fiber optics, there can exist more complicated structures, even like in this kind of polar distribution, like for example, a donut mode, where you have 0 intensity in the middle, or some kind of structures like that. Yeah, so these are the transverse modes. So the take-home message is that in lasers, in resonators, there exist transverse modes, which are related to correspond to the distribution of the optical field inside. So they translate into the output beam that we will have at the output of the resonator. And the most wanted, of course, mode is the fundamental one. So usually we want to operate in the fundamental transverse mode. So typically lasers work at the TM00 mode, but there can exist higher order modes like TM01, 10, and so on and so on. And all these are solutions of the function that describes the distribution of the electric field inside a confocal resonator. And on the next lecture, I will continue this topic and speak about stability of resonators, and then we will move on to some next fascinating topics. Do we have any questions now? Next lecture we held online in the university. So regarding to the decision of the dean, our lecture will be online through the entire semester. However, according to the regulations, the tests should be at the university, stationary. So I don't know how this will be solved technically, but I have no idea. But the lecture will be online, despite the fact that we are less than 30 people. Yeah. I thought the same, that this will be on site, but the decision of the dean was that you have today probably all classes are at home, right? So online, so that you don't have to travel to the university. They moved everything to online. Okay, so if there are no further questions, then thank you and see you next week.